We present Snap Video, a new foundation model built from the ground up for high-quality video generation. Given a text prompt describing the desired scene, our method generates the corresponding video, enabling users to express their creativity with creative scenes and compositions. Thanks to a novel video-first architecture and diffusion process, our model shines in the generation of dynamic scenes depicting challenging motion. Finally, it can generate novel views of objects by specifying circular camera motion around the subject. Let's see how this can be achieved. We identify two areas in which current video generators make suboptimal modeling choices, and we systematically address their shortcomings by applying a video-first approach to generation. In particular, we contribute a diffusion process tailored for the task of high-resolution video generation and an efficient architecture, allowing joint spatiotemporal modeling. Our method allows the generation of complex motion and fast camera changes, a difficult capability to achieve for current video generators. In recent years, we witnessed a revolution in the field of image generation, fueled by the recent advances in diffusion models and in the availability of web-scale training datasets, large-scale models, and training infrastructure. A natural idea to address the task of video generation was to extend such approaches in the time dimension. While demonstrating the feasibility of creating large-scale text-to-video models, these approaches present a number of shortcomings which do not allow the generation of high-quality motion and that we systematically address in this work. We begin our analysis from the diffusion process. Diffusion models model generation as a progressive denoising process from pure Gaussian noise to a clean sample, where a learnable model is responsible for the denoising operation. The schedule of such process in terms of the evolution of the ratio between the signal and the noise, called SNR, is a fundamental design choice, and intensive efforts have been dedicated to the tuning of diffusion processes for the image modality. Thus, such optimal SNR schedule should be preserved. However, directly applying an image diffusion process to videos would alter such schedule. Consider the example of a video where the same noise schedule is applied. Given the similarity of content between successive frames, the denoising model now has a trivial way to recover a version of the video with higher SNR by simply performing averaging of the video frames. We counteract this phenomenon by rewriting the EDM diffusion process and introducing a scaling factor that reduces the intensity of the input signal, restoring the optimal SNR throughout the diffusion process. Due to the scarcity of annotated video data, a common approach in training video generators is that of jointly training with image and video modalities. Due to the absence of repeated frames, however, images would require a separate diffusion process to avoid SNR mismatch, creating a gap between the image and video modalities. To reduce this gap and blend the two modalities, we introduce a variable frame rate training procedure for the video modality and treat images as infinite frame rate videos, to which the same diffusion process as videos can now be applied. Note that with this strategy in place, both video and image modalities feature the same SNR schedule. We ablate these changes and show image and video quality metrics computed on a test split of our video data. Using our revised diffusion process with scaled input results in consistent performance gains, and similarly, we observe that treating images as infinite frame rate videos results in better frame quality. Equipped with our new diffusion process, we turn the attention to the employed model architecture. Diffusion-based image generation methods have widely shown the effectiveness of the UNet architecture in this task, which performs the denoising process through a series of spatial computation layers. It is thus a natural idea to extend it to video generation by repeating the spatial computation for each frame and inserting new temporal computation layers interleaved with the spatial computation layers. This approach, however, suffers from two significant shortcomings. First, the replication of the computation for each frame poses a very practical limit on model scalability, a primary factor for high-quality generation. Second, we argue that the lack of joint spatiotemporal computation, which is computationally prohibitive for high-dimensional videos, limits the capabilities of the model in generating high-quality motion. Inspired by recent advances in transformer-based architectures, we make the observation that video frames possess repeated content which is amenable to compression. We thus propose a novel architecture based on FITs that learns a compressed representation of the input video, efficiently performs a joint spatiotemporal computation on the compressed representation, and finally, decompresses the results. Let's take a look at our FIT architecture. It considers an input video and divides pixels into separate groups, here highlighted with different colors. Each group is projected to a sequence of patch tokens. We then successively apply FIT blocks to the patch tokens. Each block first performs a read cross-attention operation that reads information from patch tokens into a small set of latent tokens. The small dimension of the latent representation is the key to achieve efficient generation. A cross-attention operation reads conditioning information such as text conditioning. The latent tokens successively undergo a series of self-attention operations that jointly model spatiotemporal relationships, a key component to high-quality video generation. After self-attention, latent token information is written in the patch tokens to a cross-attention operation. Finally, the patch tokens are projected back to the pixel space with a linear projection operation. The proposed architecture allows us to achieve significantly improved training and inference times while improving generation quality, which enables us to efficiently scale the model. We compare a small FIT architecture with 500 million parameters against traditional UNet architectures extended with temporal attention operations. Our model improves frame generation quality while improving more than 3 times and 4 times respectively on train and inference speed, giving substantial space for model scaling. Thanks to this efficiency, we scaled the model to 3.9 billion parameters, further improving generation quality while maintaining an inference time comparable to the UNet baselines. We perform user studies against a set of baselines where users are asked to express a preference in terms of photorealism, video text alignment, motion quality, and quantity. For publicly accessible baselines, we generate videos according to a set of 65 prompts eliciting dynamic scenes. For inaccessible methods, we compare against the samples publicly released by the authors. Our model outperforms all baselines in terms of motion quality, a finding we attribute to our joint spatiotemporal modeling approach, and performs strongly in terms of photorealism and video text alignment. When compared to publicly accessible methods, we note that baselines tend to produce still videos or videos with motion artifacts, while our method produces vivid and high-quality motion. When compared to closed-source models, we note higher quality motion and absence of flickering. Read our paper and see the website for more details.